Have you ever pondered the true essence of time and space? It's a complex, enigmatic puzzle, a riddle that's been a constant source of intrigue for the human mind. Time and space, two distinct entities, yet so intricately intertwined, they form the very fabric of our universe. They're not separate, but fused into a four-dimensional continuum, a concept we refer to as space-time. At the heart of understanding this enigma lies the theory of general relativity, a groundbreaking theory that has shaped our perception of the universe. This theory was the brainchild of one of the most brilliant minds in the history of science, Albert Einstein. His revolutionary ideas have not only challenged but fundamentally changed the way we perceive the world around us. But what exactly is general relativity, and why should we care? Well, as we delve deeper into the mysteries of the universe, this theory helps us unravel the cosmic tapestry that binds time and space. In its simplest form, general relativity is about gravity. But what is gravity? We all experience it daily when we drop a pen or jump and land back on the ground. But there's much more to it than that. Think of a trampoline. Now place a heavy bowling ball in the center. What happens? The weight of the ball distorts the trampoline, creating a dip or curvature. Anything moving across the trampoline is drawn towards the ball, not because of any pull from the ball itself, but because the path it was moving on has been distorted. That's general relativity in a nutshell. It's a theory proposed by Albert Einstein, which describes gravity not as a force that pulls objects towards each other, but as a result of the curvature of space-time caused by mass and energy. In this context, space-time is a four-dimensional model combining space and time into a single continuum. Picture the universe as this giant trampoline, and the bowling ball as a massive object, like a star or a planet. The massive object distorts the space-time around it, creating a gravity well. Other, less massive objects moving in this area, such as planets or spacecraft, are drawn towards the massive object, not because it's pulling them, but because it's literally curved the space they're moving in. But it's not just large objects that cause space-time to curve. Everything with mass or energy, from the biggest star to the smallest particle, distorts space-time to some degree. And the more mass or energy it has, the greater the distortion. This theory revolutionized our understanding of gravity. It moved us away from the Newtonian view of gravity as a force, and towards the idea that gravity is a distortion of space-time itself. It's a concept that might seem strange and abstract, but it's been confirmed by numerous experiments and observations. So gravity is not just a force, but a distortion of the very fabric of the universe. Imagine space-time as a river that's continually flowing downstream, representing the inexorable march of time. Now, envisage objects as boats on this river. They move downstream, which signifies moving forward in time. However, these boats can also traverse across the stream, signifying movement in space. This metaphor forms the basis of the river model of general relativity, a fascinating way to understand Einstein's groundbreaking theory. In this model, the boats, or objects on the river of space-time, are always moving. They can't simply stand still. Even if they stop moving across the stream, they're still being carried downstream by the flow of time. Now, here's a twist. The speed and direction of a boat can actually change the way it experiences time and space. For instance, a boat moving rapidly downstream will experience time at a slower pace than a boat that is relatively stationary. This is akin to the concept of time dilation. The faster you move through space, the slower you move through time. Similarly, a boat that attempts to cross the stream diagonally, moving both downstream and across the stream, will experience space differently compared to a boat moving straight downstream. It might find that it has to travel a greater distance to reach the same point on the opposite bank. This demonstrates how movement through space can warp our perception of distance. In the grand scheme of the universe, the river of space-time is not flat and calm. It's warped and curved by massive objects. Think of them as large boulders in our river. These boulders create whirlpools and rapids, causing nearby boats to change their paths and speeds. This is a representation of how gravity works in general relativity, as a curvature of space-time. So what does this all mean? It's a reminder that our everyday perception of time and space is just a small slice of a much more complex reality. It's a reality where time can slow down and distances can stretch, all depending on how we're moving through the space-time river. So time and space are not as constant as we might think. Now, what happens when a massive object spins in this river of space-time? Well, let's dive into the mesmerizing world of frame dragging and time dilation. Picture a spinning ball submerged in water. As it spins, it drags the water around it, creating a swirl. Now replace that ball with a massive object like a star or a planet, and the water with the fabric of space-time. That's frame dragging for you. The spinning object drags space-time around with it, creating a whirl of gravitational pull. But what about time dilation? It sounds like a complex concept, but it's not as intimidating as it seems. Imagine you're standing near a massive object. Because of the object's immense gravitational pull, time would actually move slower for you than for someone further away. This is not a trick or an illusion. It's a real measurable effect. It's like your clock has been put on a cosmic slow-motion setting, all thanks to the gravity of the massive object. Now, let's put these two concepts together. A spinning object not only drags space-time around with it, but also slows down time. This combined effect is known as the Lenz-Thirring effect, named after the scientists who first proposed it. So if you were near a spinning star or planet, you would not only feel the pull of the gravity dragging you around, but also experience time moving slower. You would be caught in a cosmic dance, twirling around the object while your watch ticks at a leisurely pace. Remember, this isn't science fiction. These effects have been observed and measured by scientists. In fact, the GPS system we use every day has to account for time dilation to work accurately. If it didn't, your GPS coordinates would be off by several kilometers. In the realm of general relativity, time and space can warp and twist in mind-bending ways. So the next time you glance at your watch or gaze at the stars, remember the cosmic ballet that's occurring out there in the vastness of space-time. It's a dance of gravity, time, and space that's as beautiful as it is complex. But what happens when massive objects in space move, collide, or explode? This ballet of cosmic forces gives birth to something quite intriguing: gravitational waves. Imagine a stone being dropped into a pond. The stone disrupts the calm surface, creating ripples that spread outwards. Now picture this on an inconceivably grander scale, where the pond is the fabric of space-time itself, and the stone, a pair of coalescing black holes. Gravitational waves are these ripples in space-time caused by the acceleration of massive objects. Just as the movement of a boat creates waves in water, the movement of massive objects like stars and black holes generates waves in the fabric of space-time. These waves aren't confined to their local environment. They radiate outwards, traveling at the speed of light, subtly stretching and squeezing space as they pass. Now, it's important to note that these waves are incredibly weak. They don't cause the stars to wobble, nor do they shake the Earth. In fact, they're so elusive that for a long time they remained purely theoretical. That is, until the year 2015. In 2015, an international team of scientists working on the LIGO project, that's the Laser Interferometer Gravitational Wave Observatory, made an unprecedented discovery. They detected the faint echoes of a cosmic cataclysm, the merging of two black holes, a billion light-years away. This detection, a monumental feat of scientific ingenuity, confirmed Einstein's century-old prediction and ushered in a new era of gravitational wave astronomy. So why does this matter? Well, gravitational waves give us a completely new way of observing the universe. They allow us to listen to the cosmos, to detect events that would otherwise be invisible to traditional telescopes. They open up a world of cosmic whispers, echoes from the most violent events in the universe. Gravitational waves are the whispers of the cosmos, carrying stories from far across the universe. They are the cosmic messages we're just beginning to decipher, and who knows what secrets they might reveal. So why does general relativity matter in our daily lives? Well, quite simply, it is intricately woven into the fabric of our modern technology and understanding of the universe. For example, the global positioning system technology that we use daily to navigate our world relies on principles of general relativity to correct for the time dilation effect, allowing for pinpoint accuracy. Then there's the fascinating realm of black hole research, made possible by the predictions of general relativity. This research not only captivates our imaginations, but also provides crucial insights into the nature of space-time and the extreme conditions of the universe. Finally, general relativity shapes our understanding of the universe's history and future. It's the framework that allows us to study the Big Bang, the expansion of the universe, and even its potential fate. While general relativity might seem abstract and distant, it is a cornerstone of our understanding of the universe and has tangible impacts on our technology and worldview. General relativity opens a door to a universe far more fascinating and complex than we might have thought. This theory, which once seemed so abstract and distant, breathes life into our understanding of the cosmos. It has shown us how the river model of general relativity can visualize the warping of space-time, how frame dragging and time dilation can alter our perception of reality, and how gravitational waves ripple across the universe, unseen but not unfelt. These concepts, though complex, unravel the enigma of time and space, simplifying the mysteries of the universe into digestible bits of knowledge. But remember, we've only just scratched the surface. There's a whole universe out there waiting to be discovered, waiting to be understood. So let's not stop here. Let's continue to challenge our understanding, to push the boundaries of what we know. The universe is a symphony, and general relativity is the sheet music. So keep listening, keep learning, and keep exploring.